section 3.3, to apply the properties of the unit circle and to evaluate circular functions. Our first slide starts a definition of a unit circle. A unit circle has its center at the origin and a radius of 1 unit. Here we're given a diagram that we have seen in previous sections where I have a coordinate plane, a circle on my coordinate plane, and we have a angle that is centered at the origin. My initial side of the angle is on the x-axis. We have a theta written in radian measure that goes to a terminal side of the axis, and on that circle we have a point that has a value of x and y. What they're going to tell us, though, is that the measure of r, or the radius of this circle, is equal to 1 unit. And that is defined down here by the formula for a circle, x squared plus y squared, and our r, or radius, is 1. So the main thing to keep in mind here is that when I have a unit circle, that the radius of that circle is always going to be 1 unit. Let's keep in mind from previous sections that we know that s, which is the arc length, is equal to the radius times theta, as long as theta is written in radian measure. But let's also know that we combine that with the unit circle, that r is going to be 1 unit. So s is equal to 1 times theta. So s in the unit circle is related to theta in that they are numerically equal. When this occurs, these are called circular functions. This diagram also shows these circular functions, at least the beginnings of some of our trig circular functions, that x is equal to cosine s and y is equal to sine s. Let's take a look at how these trig functions are related to the circular functions. As in previous sections, we know that sine theta is equal to y over r. But when we add this to the unit circle, we know that theta is equivalent to s, or the arc length. So sine of s is equal to y over r, but on the unit circle, r is always 1. So sine s is equal to y. Now that we have this, we can find the reciprocal function, which is going to be cosecant s, which is the reciprocal of y, which gives us 1 over y. And of course, y is not allowed to equal 0. We can continue with cosine of theta equal to x over r. And in the unit circle, cosine of theta, which is equivalent to s, is equal to x over r, but recall r in the unit circle is equal to 1, so cosine s is equal to x. The reciprocal function is secant s is equal to 1 over x, and x is not allowed to equal 1, and the remaining function would be tangent of theta is equal to y over x. Therefore, tangent of s, theta and s being equivalent, is going to be y over x. And the reciprocal function is cotangent of s equal to x over y. The next slide shows us our circular functions that I've generated on the previous slide. So here you see, as before, sine of s is y. Cosecant of s is 1 over y cannot equal 0. Cosine of s is x. Secant of s is 1 over x, where x cannot equal 0. Tangent of s is y over x cannot equal 0, and its reciprocal function, cotangent of s, is x over y, where y is not equal to 0. I placed this slide under our group resources under Chapter 3. The next slide shows us the unit circle in its entirety. I put this diagram under Chapter 3 resources on our group page. If we take a look at the diagram, it seems overwhelming with all the information that is given to us. What I need to do is show you how this unit circle is generated and show you that these values are similar to all the examples we've done in the previous sections. And hopefully, after I've done that, it doesn't seem so overwhelming. Let's start forming our unit circle by starting with the first point on that unit circle. I created an initial side of an angle on my x-axis. I drew a terminal side of an angle to that point I wanted to start with. That point is going to be at 30 degrees, or also pi over 6. So I want to see how they generated this point on the terminal side of my angle. Notice also, when I created my angle, I did drop a vertical. This is very similar to all the problems I've done in the past. That gives us a right triangle that is generated inside my unit circle. So let's go to another page and see how we actually perform the operations to get that point. From the previous slide, I generated a 30, 60, 90 right triangle inside my unit circle. Here I've done the same, and recall that I can convert a 30-degree measure into radians by multiplying 30 by pi over 180. And when I do that, that will give me pi over 6. Knowing that this triangle is in the unit circle, I know that the terminal side, or radius of the terminal side, is equal to 1 unit. Knowing this, I can determine the other values of this triangle by knowing the special right triangle rules in this 30, 60, 90 triangle. Recall from that video that I need to determine the short leg of this triangle first. To do that, I'm going to take the hypotenuse and divide by 2. So here, I'm going to get 1/2. And when I refer back to my unit circle, this will give me my y value. Now that I know my short leg, I need to determine the long leg, which is opposite my 60-degree angle, by multiplying this value by the square root of 3, which will give us the square root of 3 over 2. Referring back to my unit circle, this will give me my x value. Now, I can relate these values into my circular functions. Recall that I have the sine of s, and in this case, it's going to be pi over 6, is going to be the value equal to the y. So here, sine of pi over 6 is 1/2. Cosine of pi over 6 is equal to the x value. Here, that's the square root of 3 over 2. And tangent of s is equal to y over x, which will give us 1/2 divided by the square root of 3 over 2. And when I continue simplifying, this is going to be 1/2 divided by the square root of 3 over 2, which equals 1/2 times 2 over the square root of 3. But when I simplify, that gives me 1 over the square root of 3. Then I need to rationalize. And that will give me my answer for tangent of s, which is pi over 6, equal to the square root of 3 over 3. If I refer back to the unit circle, that generates our point on the terminal side of a 30-degree angle, which is equal to my x value, which is square root of 3 over 2, and 1/2. Now, this unit circle seems very complicated, but if I just create angles inside this unit circle, for example, 150 degrees, which if I convert to radians would be 5 pi over 6, then if I find a reference angle for 150 degrees to my x-axis, that will give us a 30-degree angle. The 30-degree angle is going to give us the same terminal point, but all I need to do is determine what are my sines of x and y inside of quadrant 2. Here, I'm going to have the square root of 3 over 2.5 at 150 degrees, but my x value is negative. That's similar if I create an angle that is 210 degrees with the reference angle of 30 degrees. Again, notice the values are all the same for that 30-degree reference angle. I just need to determine what is going to be the positive and negative. In quadrant 3, x is negative and y is negative. And if I create another angle which is 330 degrees, I'm going to be in quadrant 4. A reference angle is going to give me another 30-degree angle. Again, my values are the same, but I just need to determine the positive and negative. Here, x is positive and y is negative. And now that I have these three functions, I can determine the reciprocal functions of cosecant, secant, and cotangent by taking the reciprocal and following the constraints generated by the previous slides that I cannot have a zero in the denominator.